reduction. Let's remember what augmented coefficient matrix is. It's basically a matrix that is obtained by appending a matrix of coefficient and vector of constants. So all these row reduction that we want to do is on this augmented matrix, basically. And let's say example of this, if I have ax plus by equal to c, and then dx plus fy equal to g, the augmented matrix looks like this. A, B, D, F is the matrix of coefficient. Put a line in here. C and G as the vector of constant. So elementary row operations. These are the elementary row operations. One is interchanging rows. Again, if you remember, this sound like row. So we're going to use that. So we can do row I with row j. Or multiplying a row by a non-zero constant. So if c non-zero, then c and let's say row I is going to be put in row I. Adding a multiple of one row to another. That could be c times row I plus row j goes into row j. So now we do all these elementary row operations, and last time we saw that. We used it to find the row echelon form of the system, basically linear system. There's more to it. So two linear systems are called row equivalent if one can be obtained from the other by finitely many elementary row operations. So the fun part of this is, and we talked about it last time a little bit, when you have two linear systems that are row equivalent, they actually have the same set of solutions. If one has and one is consistent, the other one has to be consistent as well. So then this theorem is allowing us to say, hey, this row echelon form, and today we learn reduced row echelon form, actually whatever solution we get from them are the solution to the original system. So let's remember what the row echelon form is. A matrix is in row echelon form if all non-zero rows are above all zero rows. And if the first non-zero entry, and we call that leading term or leading entry, of a row is to the right of leading entry of previous row. And finally, all entries below a leading entry should be zero. So let's look at this. Basically, if you start and you have a leading entry 1 in here, and then and all the underneath it should be 0. Then on the second row, you have to move on to the right at least once to have a leading entry. Let's say 1 here. And then on the third row, because leading entry on the second row is in the second column, you have to have a 0 in here also, and you move on to at least here. It could be that you move on to the fourth row and you have a leading entry there, and so on. And then if you have a row of all 0, it has to be on the very bottom. You can't have all zeros up here, basically. That is bad. So it's sort of the leading entries step toward the right side of the page. The next thing is a reduced row echelon form. So it is a row echelon form where leading entries are 1. I like to even choose 1 in the row echelon form, but in the definition, the reduced row echelon form has leading entry 1, and all entries above it we call the leading entries in row echelon form, reduced row echelon form, leading 1 or 0. Now consider this matrix and first verify that it actually is a reduced row echelon form. See if it's echelon form. So all rows of all 0 are on the bottom. There is nothing underneath them that is non-zero. So all rows of all 0 are below rows, non-zero rows. And then there's a leading 1. All leading terms are leading 1s. Leading terms are the non-zero, the first non-zero entry. What else do we know? The leading terms are moving. Leading terms are moving this way as we move that way. What else is there to check? All entries above and below a leading one is 0. So if this matrix is a reduced row echelon form of an augmented matrix, find the associated system. So this is how we do it. Basically, if it's augmented, we're gonna draw the line and then assign variable to each column, x3 and x4. So then basically the first row becomes 1 times x1 plus 0 times x2 plus 2 times x3 plus 0 times x4 equal to -3. Row 2 is 0x1 plus x2 plus 4 times x4 equal to 6. So everything on the right of the line that attaches the coefficients to constant vector are going to be constant. Everything to the left have to multiply the x1, x2, x3, x4. And then it's asking you to solve the system. Here I can say that these two columns, column for x1 and x2, have leading 1. But the columns for x3 and x4 don't have leading 1. See, this is leading 1, this is leading 1. I probably should have chosen the red, swap the red and green. And so these two columns don't have leading ones. So I'm going to choose these two variables as free variables. It's another word for maybe independent variable. So what I'm going to do is I start basically assign a parameter to each of them. For x3, I go s. For x4, I go t. And then I solve for the other variables, basically. And I start from bottom to top, always. In this case, it doesn't matter, but a lot of times it does. And so the last row gives me x2 plus 4t equal to 6. So I get x2 is equal to 4 equal to not 4, but if you solve, you get 6 minus 4t. And then this is the second row. Then you go back to the first row and x1, now put the parameter in it again, 2s instead of x3, and that is equal to -3. And then you solve for x1, which is -3 minus 2s. Now what happens? Basically, x1 is -3 minus 2s. x2 is 6 minus 4t. And then we assign parameters to x3, which is to x3 and x2. We assign parameters x4, sorry, x3 and x4. And so that's what we get. And that is basically x1, x2, x3, and x4 is equal to this. So that's the solution. Now we discuss the free parameter alongside that. So let's say um, in a reduced row echelon form, you can call it RREF. Um, any any variable whose column does not include a leading term, a leading one, leading term. We assign a parameter to those. Three variables. So solving when you have a free variable, assign parameters and solve for other variables. Um, Going from bottom to top. So why is reduced row echelon form preferred? You can tell that basically the reduced row echelon form, as you move up, each equation contains only one not free variable. So let's decide which of this following is not in row echelon form. And how do we do that? Um, I'm looking at these and I notice over here, leading one is to the right of the one below it, or the third row's leading one is to the left of the row before it. And so this is the one. This has an easy fix. I can swap row 2 and row 3. So the process of basically using elementary row operations to obtain a row echelon form is row reduction. What is rank? The rank of a matrix in reduced form is the number of non-zero rows in either one. It doesn't matter if it's reduced row echelon form or row echelon form, and I want to use Rref. So the number of equations can be reduced to less than the number of variables. And that is okay. And that typically means that there's no unique solution. It's either inconsistent or infinite solutions. If a leading term is the last term, that is at the very last column, the system has no solution. It's inconsistent. And that's like the same thing as saying that basically things on the left hand side is all zeros and it's going to be equal to 1, and that's just not possible. If none of the leading terms appear on the last column, then the system is consistent, because then you can solve for all the variables. So in terms of uniqueness, row echelon form is not unique, but reduced row echelon form is unique.